In this module, we are going to look at polyprotic acids. Our objective for this module is to be able to identify polyprotic acids as well as write the ionization reactions for each step. What distinguishes polyprotic acids from monoprotic acids is in the protons. In this case, we have multiple protons that are ionizable from this particular molecule. Here we have H2CO3 that has 2 protons and therefore it can undergo 2 ionization steps. The first step will remove 1 proton and produce HCO3 minus. Then HCO3 minus will lose its proton and form H plus and CO3 2 minus. Notice that each step has its own Ka value, and one thing we notice is that Ka2 for the second reaction is much smaller than Ka1, and this is a trend that will continue whenever we look at polyprotic acids. Here are some examples of some common polyprotic acids. We've already seen H2SO4, and what we notice is that our Ka value is much greater than 1. Remember that the first ionization step of H2SO4 is actually representative of a strong acid. The second step is not. The second step is a weak acid, and as such has a Ka value, even though it's considerably higher than many other Ka values we see for a second step. Sulfurous acid has 2 ionizable protons, so it has 2 Ka values. Carbonic acid also has 2 Ka values for each of its ionizable protons. Phosphoric acid actually has 3 ionizable protons, and for that it has 3 Ka values. Notice that the trend we saw with carbonic acid, that Ka2 is less than Ka1, continues as we go to phosphoric. Ka3 is the smallest of the 3 values. Ka2 is a little bit bigger, and Ka1 is somewhat larger. We will see this trend continue for all polyprotic acids. Let's look at an example. Which of the following best describes the pH of a 0.03 molar H2SO4 solution? Will the pH be less than 1.5 or greater than 1.5? When we look at H2SO4, we need to remember that it ionizes in 2 steps. The first step, H2SO4, is a complete reaction and complete ionization to H plus HSO4 minus. Remember, this first step is a strong acid step. Then we have HSO4 minus in equilibrium with H plus and SO4 2 minus. If I go back to my problem, I know that the H2SO4 concentration initially is 0.03. Therefore, after the first ionization, the H plus concentration for my first step will be equal to 0.03 molar, the same as the initial concentration of H2SO4. And if I were to find the pH only from that amount of H plus, I would take the pH equals the negative log of 0.03, and I would find that pH equals 1.5. However, I do have a second step that's producing a little bit more H plus. Now we don't know the exact amount, so we can't quantify what the pH is, but what we do know is that with the second step, the H plus concentration is increasing, if only slightly. It is increasing, and therefore the pH must be decreasing because we have a solution that is more acidic, more H plus, therefore the pH value will decrease. If you're not sure about why that's the case, then go ahead and put in a different number that is greater than 0.03. For example, what if we said H plus was equal to 0.04? Then we could say that pH equals the negative log of 0.04, and what we find is that pH equals 1.4. So as we've increased our H plus concentration, we've decreased the pH of the solution. In the next module, we'll look at different types of acids and the periodic trends related to their strength.